Okay. Okay, let's see if the clicker is working. Excellent. Okay.
Okay, we can start.
Thanks. Right. So yeah. So with the sort of starting bits sorted out, we're now going to try to do some examples, and they will sort of have slightly different flavors, each of them, but they're sort of, I tried to pick them so that they're emblematic of the type of result you get for a certain metric. Okay, so just to give a starting point, so many Markov chains with a bit of idealization at some stage will satisfy curvature conditions, and you can get good explicit constants in terms of bounding them. Here, I'm going to try catalog some examples of cases which are pretty transparent to do the analysis of, where hopefully, a week down the track, you will remember 30% of the proof or something like this. Yeah, the choice of examples is guided by the sort of collective interests of the people in this room, which means things like Monte Carlo for statistical computations, which means that things like random walks on graphs are not necessarily as interesting, but things like diffusions and HMC are a bit more. Yeah, so I think I have sort of 3 or 4 sort of themes, let's say. Okay, so some advice for how to go about proving results like this, basically. On your first try, especially if you're working with a sufficiently general algorithm, make very generous assumptions to yourself and check if you can prove it in that case, right? Work with strong convexity and compact sets and everything like this, and you will tend to get a lot of insight on what needs to be going well, right? For calculations, it's often useful to work with continuous time processes. So here I'll give some examples of continuous time diffusions, where just working with things like ODEs makes life much easier for you than discretizations, although in these specific cases, the discretizations are not so bad. Another general principle would be, often in interesting cases, you'll be studying some high-dimensional process, and if you can reduce the contractivity problem to studying a lower-dimensional problem, your life becomes easier, right? And so typically what happens is, if you can look at the distance between the 2 chains you're trying to couple and show that that satisfies an ODE up to some inequality or so, that makes your life easier. And then the sort of 4th piece of advice, which is not really about this section, but the subsequent one, is that as problem gets harder, you should be more flexible about what metric you want to show contractivity in. Okay, and we'll sort of give more examples of that later, but for this section, many things will be friendly to us. Okay. First one, curvature in the discrete metric. So our discrete metric is the sort of very boring one, where the metric is only 0 when the points are the same, and otherwise it's 1. Okay. And so in this context, we know, and I think Matt mentioned this briefly yesterday, that the Wasserstein distance with respect to this metric is just the total variation distance, okay, which has this nice coupling interpretation, as is common in this field. And so in this case, the contractivity condition says, if I have 2 distinct points, and actually that's not even really a condition, you'll see, that the total variation distance between the 2 kernels is bounded away from 1 like this. Okay, so there's not even any sort of d of xy on the right-hand side, because it's always 1. Okay. So now you can sort of think of this, if you imagine sort of your mental picture of measure space, right? You have a bunch of kernels p of x dot, right? And you know that for any 2 of them, they're within 1 minus kappa of one another, so somehow the diameter of that space is bounded, right? These collections of p of x dot. And so it means in particular that there is a probability measure that they're all uniformly close to, right? All of these kernels are close to one another, and so there's some sort of centroid they're close to. In particular, there's some probability measure nu, such that for all x, the total variation distance between p of x dot and nu is bounded away from 1, right? And so people who've sort of seen things like minorization conditions will realize that this is equivalent to one of those, right? So it means no matter where I am in the space, with probability kappa, I can couple my draw from p of x dot with a draw from this measure that doesn't depend on x at all. Okay, so it's a very strong condition, right? And so you'll see this referred to in the literature as a Doblin condition or a minorization condition, sometimes with the caveats that it's a uniform minorization because it holds for all x, or that it's a one-step minorization because this can sometimes hold not for p, but for p to the some power k, let's say. Okay, so this I think is about as strong as a curvature assumption can get, right? No matter where you are in the space, it doesn't actually matter at all. You can couple in one step. Okay, and so the concrete example for this is, yep.
Can you give the intuition for mu again?
So So think in the measure space, you have all of these P of x dots, right? There are a bunch of points. We know that they're all close to one another, and so in principle, you could pick a centroid of these things and say they're also all close to this thing. But the point is that it doesn't depend on x. That's good. Okay, so the application is to the independent metropolis Hastings.
Yep. Think P of x, you have a bunch of them. As in we change x.
So for each x, there is a kernel P of x dot. Yeah. Cool. So the independent metropolis Hastings is sort of pretty early doors NCMC algorithm, which is global in some sense, which means that perhaps it's well suited for a global metric like the discrete metric. So in this example, we have a target distribution pi and a proposal distribution q. And we're going to assume that the Radon-Nikodym derivative of pi on q is bounded above by some constant m. Okay, so this is sort of the situation where in principle rejection sampling would work, but you don't know what the right constant would be. So it's something you can still implement. And so you can define a pi invariant Markov kernel P by using Q as a metropolis Hastings proposal here, right? And so this is sort of what the kernel looks like in measure form. Algorithmically, it says you draw a sample from Q, we call that Z. You evaluate this probability, alpha of x and z. With that probability, you accept the sample and you move there. Otherwise, you stay in your current state. And these definitions down the bottom are not. The second one's not crucial, but it just is needed to make the statement. Okay, so this is a Markov kernel, and we're going to show that with this m being finite, we have a uniform minorization condition. We have curvature in the discrete metric. Okay, so this is something that's been proved in various forms over the years. Okay, so I'm writing W for the Radon-Nikodym derivative here. So we've assumed that this is bounded above by n, uniformly in x. So that means we can always lower bound W of x inverse using the naive bound. And so what we're going to try to show is sort of bound this acceptance rate from one state to another from below. Right? So we have this 1 over Wx in the first term. There. Right? So we're going to bound that from below, giving us this inequality here. Right? And then actually we know W of z is bounded above by m. So this second term here is always the smaller of the two, which means we can pull it out. And so we can directly bound the acceptance rate just as a function of the place that we're moving to. Okay, so with no dependence on x, which is nice. So that means that the probability of moving from x to another state is at least the probability of proposing that state and accepting it. So we're ignoring the chance that we're possibly there already. Right? Then we use our estimate on the acceptance probability here. And then we use the definition of W as the Radon-Nikodym derivative to show that we have a minorization condition with respect to pi. Okay? So we have, no matter where we are in the space, there's at least a probability 1 over m of coupling with a draw from pi. Okay? So actually, this is sort of even stronger than curvature. It's like you get a perfect sample in that stuff. Okay, but from these calculations, we get that the IMH has curvature at least 1 over m with respect to the discrete metric. Okay, and actually, this is known to be sharp. There's sort of many proofs of it by now. And people know sort of things like the spectrum of the IMH and other things like this. Okay, a natural thing to say is the IMH is not necessarily a super interesting algorithm because it applies in the case where rejection sampling works, which is pretty niche already, right? What's nice is that there are other algorithms which sort of on their face look like different algorithms, but are equivalent to an IMH on a sort of more complicated space. And so things like the iterated sampling importance resampling or the iterated conditional SMC also fall under this umbrella. Now, okay, in these situations, you still need strong assumptions to say that you have the bounded weights. But these theorems really do apply. And in sort of the sharpest theorems they have for particle Gibbs and iterated conditional SMC, there are minorization conditions like this being used. Okay. So it's as the story is often the case, it's a strong assumption, but it's sort of the best we can do in many cases. Yes, I can. Yep.
How do you conclude that m to the minus 1 is a curvature?
So sorry, so that I have sort of glossed over that slightly. So so this condition here implies that you can write P of x dot is at least kappa times nu dot for all x. Okay.
Oh, and that's what you have.
And then that's what we've proven here. Yeah, I should have made that more explicit. Thanks. Okay, so that's our first example, but we're really getting the right rate. Okay, so we've done a good, honest analysis, even if the algorithm is a bit narrow in some ways. Okay, so now I can move on to some things which are maybe closer to what we have in our heads when we imagine transport methods. So curvature in the Euclidean metric. I think in my experience, this is sort of the most intuitive one, right? You're imagining particles moving around the space, et cetera, throughout, work in RD, use the two norm. Some of the examples will be in continuous time, some will be in discrete time. It just depends on how easy it is to get the estimates, but we'll see. In the Euclidean case, it also seems to be disproportionately the case that you can have a stronger property. So throughout, we're working with the curvature assumption, which says on average we can shrink the distances, right? But actually, there's various cases where you can get contractivity deterministically. No matter what the random noise you pump into the system is, the points get closer together by this rate. And it turns out that in many cases, this lets you get even better results out at the end, but it's somehow much less robust. And so I won't dwell on those too much. Yeah, this is not always realistic, but it can be insightful to study, particularly if you're looking at comparison and perturbation results, right? You first study the very nice thing, and then you come back down to earth a bit. It's sort of interesting that to get these stronger results, the proofs are often easier because you've used such strong assumptions, basically. And as I said, the consequences can be quite a lot stronger. So I think some of my examples will have that feature and some won't. We'll sort of see it as we go. Okay, so here's the example I mentioned earlier when Saf asked this nice question. So we're going to work here with, so I should say throughout this, I will occasionally sort of use stochastic calculus in a bit of a hand-wavy way. I don't think it's in any of our interests to go much deeper than that. We're just doing formal calculations, and they can be made rigorous, but that's not what today is about. Okay, so today we're interested in studying the overdamped Langevin diffusion, which is sort of a nice canonical object, sort of one of the nicest diffusions to work with in many ways, as applied to sampling from a target pi, which is proportional to e to the minus v, which we will assume to be m strongly log concave, and I'll sort of make that precise if we need to. So something that is a bit like a Gaussian and then even better. So here I'm not making any smoothness assumptions or anything like this, because we don't have to discretize anything. The diffusion just happens in continuous time, and so the strong convexity will do the work for us. Okay, and so you'll see from the dynamics that you have this gradient term forcing us towards the modes of the distribution. Because of the convexity assumption, we know that there's a unique mode, etc., so everything's pushing in the same direction. And then we add in a little bit of Gaussian noise, which ensures that we have the right invariant measure. And so here's the first one where we'll actually sort of somewhat explicitly construct the coupling that we're using, right? And so I'm going to construct diffusions following this, which I'll call xt and yt, and I will essentially make each of them follow this path with the same Brownian motion, right? So each one of them is following the gradient downhill, and then the noise that you add to each of them is the same thing. So this is what's known as the synchronous coupling, because you sort of synchronize the noise that is pumped into each system. And so what's nice is that if you look at the displacement between the two paths and how it evolves in time, the noise vanishes, right? Because you're sort of saying, if I translate each of them by the same thing, I don't see the translation at the end of the day. Of course, these paths are still stochastic, but at least it's nice at this level, right? Okay, so we have that evolution. Now we look at the evolution of the squared distance between the two of them and apply the chain rule. Again, like not even any stochastic calculus at this stage. So we have x minus y, grad v x minus grad v of y. And so strong convexity is actually equivalent to the statement that this inner product here, so look at how the gradients between the 2 points align relative to the displacement between them, that can be lower bounded by m times x minus y squared. Okay, so this is nice, and so thinking of this as an ODE or differential inequality, if you like, for this quantity here, we're almost done, right? We apply Gromwell's inequality and we see that this is going to decay exponentially with time, uniformly in all of the quantities that we care about. Okay, so this is a case where you have the almost short contraction, which is even stronger than on average. And so this is sort of, in continuous time, we'd say this means it has curvature at least m, because you should sort of take square roots on both sides. Okay, so this is nice. So the way I presented it highlights the Langevin diffusion, because it's something that's a bit familiar to us and it has some nice properties. But actually, if you go back through the analysis, we didn't use almost anything specific about the fact that it's the Langevin diffusion, just that the drifts are pushing you closer to one another. And so actually, if you wanted to study another diffusion with additive noise for some other drift B, as long as it satisfies a suitable sort of contractivity condition, which is essentially going to be reverse engineering going from this line to this line, right? So this will be B of X minus B of Y. But if you reverse engineer the condition on B such that these implications hold, then you can go home again, right? And so this is something which is spelled out in quite a lot of detail in a paper of Cattier and Guillain called semi-log concave Markov diffusions. And they sort of, their point in this paper is actually the Langevin stuff and the reversibility, you don't need it for many, many results. So this is sort of interesting in non-equilibrium situations as well. So a comment which I've left in here. So in this case, right, we have what's called an elliptic diffusion, which basically means that there is noise being pumped into every direction of the system, and so we don't have too much degeneracy. There are many interesting cases where that's not true, like the underdamped Langevin diffusion, where you have noise only pumped into one of the coordinates. And this can be challenging for many forms of analysis, because things like absolute continuity of densities and stuff, you have to work harder for. It's sort of still true, but it's challenging. But the transport point of view on things is very nice, because you don't care about this. You just care about where are the particles and are they getting closer to one another. And so you can also study hypoelliptic diffusions like the underdamped Langevin with these same techniques. What is typically the case in these settings is that you need to fiddle with the metric a little bit. So in these cases, let's say you have a position and a velocity, right? Working with the direct L2 norm on position and velocity will not have contraction most of the time for these sort of degeneracy reasons. But there are often suitable linear transformations of X and V where you will have contractivity in that twisted norm. It should be said, it's not like preconditioning X or preconditioning V. It's just looking at how the position and the velocity interact with one another. So it's like you don't have to consider an n by n matrix. You really have to consider a 2 by 2 matrix and optimize over those somehow. Okay, so that's the diffusion examples. And so what else is there? So there's, I think my favorite paper on actually establishing these contractivity conditions is a JMLR paper from a couple of years ago by Chus Sansana and Kostas Sigalakis. And they show, like, under suitable convexity type assumptions, how do you systematically construct these twisted matrices so that you get the contraction in continuous time. And actually in the paper, they do a lot of interesting stuff on discretizations as well. But even without the discretizations, it's a very nice paper. And really made quite clear. It's related to some nice work in optimization in the past few years on getting sharp convergence rates for first order methods. Okay, I think that's it for diffusions for now. Yes, okay. And so the other one, which is moving back into discrete time, is what I call iterated random function systems. Sometimes people will drop various words in this and just call them iterated function systems or random function systems, etc. But to me, it's all kind of the same thing. And so it's sort of, in a way, it's generic because many Markov chains can be written in this form, but it's somehow writing it in this form is the contribution of this area, right? And so the idea is that at each step of your Markov chain, you draw a random function from some distribution over functions, which map the state space to itself, and then you apply that function to your current state. Okay? So you sample a function fn, and you move xn minus 1 to fn of xn minus 1. Okay? And so the reason this is in principle interesting is not so much how things look for one Markov chain evolving in time, but for couplings and even for sort of grand couplings, in the sense that when you specify this sequence of functions, you can show how things are moving on the entire space, right? And so this is related to things like random dynamical systems and what are called stochastic flows. But somehow it's, at some level it's very useful that you know what the function's doing everywhere in the space, and it's pushing all points into the center and so on. Rather than just, for two randomly chosen points, things go well on average. So if the Fn are very nice in some uniform sense, then you can deduce many strong things. In a way, this is even more ambitious than coupling, right? You're not picking 2 points, you're picking all of the points at once. But the theory here is very nice. Okay, so assume that your distribution of the functions is supported on functions which are almost surely Lipschitz. So every Fn that you sample is Lipschitz with some constant, possibly bigger than 1. Okay. In this case, I won't really write out the proof directly, because in a sense the coupling is obvious, right? If the Fn are good enough, the coupling is you apply the same function to both chains, essentially. And so, okay, suppose you have that almost surely under this distribution, the Lipschitz constant is bounded away from 1. In that case, you have the almost sure contraction. Things are getting better at every step deterministically, right? So that would be something like, at each step you halve the state and add some Gaussian noise. If instead you only have that the Lipschitz constant is integrable and has expectation less than 1, actually things are still reasonably simple. You use the same coupling and you do the same analysis and things go through as is. It turns out that this is quite a bit stronger than what one needs for the system to be exponentially ergodic. So actually you can show that as long as the logarithm of the Lipschitz constant that you sample has expectation less than 0, you will get an exponential rate of convergence. And more or less the reason for this is if you imagine sampling a large number of functions and taking their composition, the Lipschitz function of the composition is going to be sort of like exponential of n times the expected log Lipschitz function. So another problem I'm quite interested in, but I don't really know how to do, would be, say you have this, you know that this expectation takes some value minus c, so it's less than 0. Turn this into an actual non-asymptotic contractivity estimate in some metric. I think that would be quite nice. Because in a way, this here is a very big gap, right? It's like the difference between saying the expectation of x is less than 0 and the expectation of the exponential of x is less than 1. Right? That's a very big gap in many ways. And so I'd be interested to see that closed. But I don't really know how to do it. The second condition somehow has the flavor of like you're immediately appealing to asymptotics in a way. You're saying eventually the log Lipschitz constants will stabilize. Okay, so we'll give some examples of this. Some of them will be similar to the previous ones. Yeah, so I think I mentioned this briefly beforehand. So we had earlier this Langevin diffusion. There are various ways of discretizing it. And we sort of like to believe that if you discretize things well, then you take the properties of the continuum system and you replicate them at the discrete time level. Okay. And so the iterated random function view on what's called the unadjusted Langevin algorithm, which is maybe the de facto discretization, right, is that you sample some Gaussian noise, and then your function is the function that maps your state to state plus the gradient step plus the appropriate amount of noise. Okay, so in a way, it seems overkill to think of it as a distribution over functions, but it does give you this sort of global coupling of all states. Now, in this case, we can say, look at where this function maps your two states. Again, we see that the noise cancels out, and then by sort of applying, I don't know, like the fundamental theorem of calculus, you should have a dt here, that you can write the discrepancy between these two things as an integral of vectors. So the important thing here is that under a suitable convexity assumption, this matrix here will have its eigenvalues controlled in a nice interval. Okay, and we'll show what that is in the next step. So we're going to again assume we have m-strong convexity of the potential, and now a bit of smoothness as well. Okay, the smoothness inevitably has to show up in some form or another because we are discretizing. Okay, so the m is saying the continuous process is good, and the l is saying you can take step sizes that are not too small. And I will write q for the inverse of the condition number because it makes it sort of slightly easier to present the results. So be it, you want to think, when q is close to 0, the problem is very hard. Okay, so starting with this exact equality here, we can take norms on both sides and apply the Jensen's inequality, say, to estimate the 2 norm between the new points in terms of the 2 norm between the old points times this matrix norm. Again, I should have dt's here. And we can essentially control this operator norm using knowledge of the eigenvalues of grad squared v. Okay, and so we know that it's basically going to be less than or equal to 1 minus h lambda for every lambda in the spectrum of this matrix. And so we just upper bound this by saying the spectrum could be anywhere in here. Right? Okay, and actually with this bound here, you can show directly that if you take the step size too big, you will not have contractivity. Okay, that's sort of saying you're resolving the dynamics very poorly at the numerical level. But okay, this is sort of a piecewise linear function, and so we understand it reasonably well. And so you can show that if you take the step size h to scale like this, then you get the optimal upper bound for the contractivity, and you compute it explicitly as such. And again, this is an almost short bound, right? So you have very strong convergence properties here. And from that, you get that the contractivity is bounded as roughly 2 times the inverse condition number, which reproduces this thing we expect, that when you have poor conditioning, you have to take a very small step size that slows down the convergence of the Markov chain. And so some exercises, which I think I've not seen in papers, but are sort of natural extensions of this. So one thing would be, there is some work of Marcelo Pereira, where instead of taking a gradient step with respect to the potential V, you sort of take a proximal step, or you take a gradient step on the so-called Moreau-Yasuda envelope. So it's something that sort of regularizes the dynamics quite a bit. So in this case, you expect that you might be able to take larger step sizes because you're solving an implicit problem, let's say. But you should, again, have almost short contraction, and it would be sort of a nice exercise to do. Another one, which I think is kind of nice, would be to study certain stochastic gradient MCMC methods, right? So here, in the Euler algorithm, there's only one source of noise. It's what noise you add to the diffusion. For stochastic gradient MCMC methods, in a sense, there's 2 steps, right? You pick the many batch of data that you're going to look at, you take the gradient step with respect to that, and then you add some noise on top of it. And you can sort of see that if these individual data terms you subsample are individually strongly convex, the same argument goes through almost verbatim, right? The gradient step gives you deterministic contraction, you add a bit of noise, you can go home. Right? As you know, I've not seen these analyses in the lecture, but somehow they'd be very natural to carry out. Okay, so I'll talk a bit about just some examples I've left out here, where the proofs are a bit more time-consuming, but not so horrible. So ideal Hamiltonian Monte Carlo, right? So this is the algorithm in which you have your current location x, you sample a momentum, you solve the dynamics exactly for a certain amount of time, and you take out the position vector at the final stage. And so actually it's an interesting case here where you can get an almost short contraction, but only if you pick the time just right. With the overdamped Langevin equation, we were seeing if you take more and more steps, things get better and better. But with HMC, if you integrate for too long, you can get further away again, basically. And so the argument to get the contraction there is quite a bit more careful somehow. But so that's work of Chen and Van Pala, I think. And so they prove it, again, it's in the well-conditioned potential space, so strongly convex gradient Lipschitz. But that's a very nice result. And actually, in a way, the main contribution of their work is showing how long you can safely integrate for, basically. So there were previous works that sort of showed you had contraction on small time intervals, but here they get it right up as big as you can. Although one interesting thing is that in this case, even if you do this analysis, it doesn't show clearly that it would be a better thing to do than just pure Langevin Monte Carlo, which I think conflicts with some people's intuition. So, another example, which I sort of looked at a bit because I thought it was a bit different, was to study some of the stuff people are doing in ergodic theory with deterministic dynamical systems. And so what's interesting is that in these systems, the forward dynamics tend to have Lipschitz constant greater than 1 everywhere in the space. So any 2 points repel from one another and you have sort of dynamical chaos. And so you'd think it's the worst possible fit of these things in some way. But what's very nice is that if you look at the dynamics backwards in time, right? Instead of saying, no matter where I am, I sort of diverge a bit, you say, going backwards in time, I pick between the 2 possible things I could have come from, okay? And there you get the contraction, okay? And so what's nice there is that actually, if you only care about getting a spectral gap estimate, for example, the spectral gap of the forward process and the backward process are the same thing, okay? And so you make your life easier by saying, I will study the backward process where everything's contracting, do my estimates there, and then come back. So a nice example in this case would be, you have the dynamical system on the interval 0, 1, where you map yourself to, you multiply yourself by a certain integer, and then you reduce mod 1, right? And in this case, the backwards dynamics is you pick a random interval of length 1 over k, say, and then move into it appropriately. And so you get very nice results here. Not quite as relevant to our stuff unless you want to be very fancy about sampling the uniform random variable that you use to make metropolis decisions or something like this. But it would be interesting to see more applications. I mean, I think many people have this experience of as a Monte Carlo person, you read some ergodic theory stuff and you think, oh, it would be great if I could make this useful. And it still hasn't really happened. Okay, so a really nice result, which actually would sort of take up plenty of time in itself, is the analysis of simple slice sampling. So this is work by Rudolf, Sprunk, and Natarovsky, I think. It's all three of them. And so they do the very nice thing of studying, so just to recap quickly, the slice sampling algorithm is basically you reduce the problem of sampling from a certain distribution to sampling uniformly under its graph, basically. So given x, you sample u uniformly on 0 up to pi of x, something like this. And so in this paper, they make the super nice observation that you can make various without a loss of generality type reductions of the problem, which mean that you only have to study simple slice sampling on a spherically symmetric target. And it turns out that by doing this reduction, you can get almost short contraction for simple slice sampling in a suitable Wasserstein metric for many cases. The idea is sort of, when you're sampling this height variable in the slice sampling set, you sort of make both chains move the same fraction up the height. And then when you're choosing where to move on the slice, you know that both of them are moving on spherically symmetric sets, right? And so you pick them both to go in the same direction at the same relative radius somehow. So this is an extremely nice construction, because I think when you think about slice sampling for the first time, many of these things are not obvious at all. And they sort of say, like, without a loss of generality, this. Without a loss of generality, this. And you then have an almost trivial problem when you write it in the iterated random function form. So that's very nice. And then another one, which I know is interesting to some people here, is so here I've given examples where you have a single particle doing a diffusion, right? You can imagine there's many interesting systems where you have interacting particles diffusing, where each one of them has their own drift, and then they have some sort of mean field couplings with the other particles. And so in the case where you have sort of convex confinement potentials, and also sort of not necessarily strongly, but convex interaction potentials, so particles are getting pulled closer to one another and also pulled closer to the center of the space, then you can get very nice contractivity results, almost surely or otherwise. So I think the earliest work on this is by Florent Malrieux, and then there's more recent works handling the non-convex case by Andreas Eberle and his co-authors. I'll talk more about their stuff in the final section. Okay, so I think that's it for the Euclidean contractions. I'll pause for a second in case you have questions. All right, and right, so example 3. Yes. Okay, so here's one which is a bit different, and which in the past I might have said doesn't seem so relevant to statistical problems, and now I'm increasingly convinced that there are relevant cases where it's worth thinking about. So let's recall the Hamming metric on the unit hypercube, which is sort of the L1ification of the total variation of the discrete metric. This is particularly relevant, at least historically, to the study of things like graphical models and spin systems. It's like the thing you use when studying the Ising model, essentially. But I will sort of try to convince you that for things like spatial statistics and related things, it could be quite relevant still. And so the algorithm we'll study throughout this section is what I'll call the Poissonized random scan Gibbs sampler, or the continuous time random scan Gibbs sampler. And the idea is as following. So for each node or vertex or index I, we have a rate 1 Poisson clock going off at exponential times. When the ith clock rings, we replace xi by a draw from its full conditional distribution. So it's really just random scan Gibbs sampling, but with exponential waiting times between events. And so the intuition one has is, if everything is independent, then after d log d clocks go off, you have an exact sample, for example. You wait until each clock has gone off once, and that takes d log d. And so the intuition that if you have sufficiently weakly dependent systems, this should mix well. But you can have interesting systems which are large but have locally weak dependence, but still have globally interesting things going on. So it's not quite saying the problem is so trivial as to, well, so easy as to be trivial, let's say. Okay, and so a very celebrated result which comes from statistical physics literature is that of Roland de Bruijn, who does the following. So I'll do this in the finite state space first, right? So for each index in our finite index set V, we're going to have a spin lying in a finite alphabet. So you can think of it as being plus or minus 1. You can think of it as being a finite set. That's a Potts model. And so we have some probability measure pi that we're interested in sampling from. Okay, and then I will write pi sub I dot given x as the conditional distribution of xi given xj for j not equal to I. Right? And so this influence coefficient c of ij, this is sort of saying if I look at things I'm conditioning on, which are equal in all coordinates except the jth coordinate, how different can the conditional distributions look, okay, in total variation? So that's what x equals y off j means, sort of saying xi equals yi for all I not equal to j. Okay. And so, you can fill up a matrix with theseCij's. It's worth noting that Cii is always 0, right? If they have the same off I and then you're only updating the ith coordinate, it's the same conditional. And so there's a nice result from diversion, which says that if you look at this matrix C and its spectral radius, so its largest eigenvalue, and for various reasons we know that exists and will be unique, if that spectral radius is bounded away from 1, then this sampler is exponentially ergodic with rate lambda less than rho of c, where I say this rate means sort of, the distance to equilibrium goes down like lambda to the t. Which is not necessarily how I always talk about rates. Yeah, and so this is sort of the sort of general version of the result. In textbooks and such, this is usually stated in terms of a particular estimate on the spectral radius, which is easier to compute by hand. But sort of for the abstract result, I think this is slightly nicer. Okay, so this is nice, and this, this is a nice way of getting convergence estimates for Gibbs samplers on graphical models with sparse connections, basically. And it's sort of, we'll do some examples of that in a second. And it's natural to look at this and say, this seems awfully particular to the discrete setting, say, because of the way I've written it, for example. But actually, in later work, it's sort of highlighted out that the discreteness of the spins has nothing to do with this, actually. The discreteness of the vertices in this graph you're working with, they do play a role, but actually, the general argument goes through much more widely. And so I think, as far as I know, this is from Li-Ming Wu, but it may sort of be implicit in earlier work. And so now we're going to have a spin system where each spin takes values in the same metric space E, right? And again, we have a probability measure. But now instead of looking at the total variation distance when things are different in one coordinate, we're going to look at the transport distance between the conditional distributions and how it compares to the distance between the components that are not equal. So if x equals y off j and the distance between xj and yj is this, how big is the numerator? And that's, again, a new influence matrix C. If you carefully go through the definitions, this is properly a generalization of what I've written on the previous slide. And again, the same result goes through. So this is really what's happening, and the fact that this total variation result holds as well is somehow a special case, which is historically relevant and relevant for applications, but mathematically, not special necessarily. Okay, and so I think I have some details of how this proof goes through on the next slide. Right, and so one way of thinking about this result is to say that sort of each coordinate-wise update is almost a contraction in something that's almost a metric, and then eventually we will stitch these together in a suitable way. So define this ith Lipschitz constant for sort of the Lipschitz constant of f with respect to fluctuations in the ith coordinate, let's say. You can think of this roughly as like, if I look at the ith partial derivative of f, how big is that uniformly over the space? And so if I write P of I for the Markov kernel, which does the conditional update according to xi given x not I, then a sort of nice sort of couple of lines, you can show that the Lipschitz constant of Pi of f can be bounded in this way. Okay. So it basically says, when updating one coordinate, the Lipschitz constant with respect to other coordinates does not go up by too much. Okay. And we know actually that the Lipschitz constant with respect to the coordinate that you are updating will go to 0. It's essentially saying you resolve that conditional distribution exactly. Okay, so you have this result, and with a bit of care, you can stitch this together. So now, here when I write lip pt of f, this is the vector of the Lipschitz constant with respect to each coordinate, right? We can show that this vector is point-wise, or element-wise, let's say, dominated by the original Lipschitz constants times this matrix exponential. Okay, so these are row vectors. Okay. And so in particular, it's worth mentioning that this is stronger than having Lipschitz contraction for a single metric. You're actually getting a whole vector of things being ordered by a whole vector of things, right? Although we will see later that you can sort of reduce it to the one-dimensional case. And so sort of this is what's happening, right? It's updating the ith coordinate is a massive contraction from the point of view of the ith coordinate, because you fix things completely. And then this estimate here sort of says, in the other coordinates, you don't make things too much worse. You pay a small price for it. Okay. So that's sort of the mathematical side of that, and then I think I'll give some concrete examples. Excellent. So one of the simplest ones to do is what's called the Curie-Weiss model. So that's a binary spin system with mean field interactions, basically. So you have an external field here, which is saying if H is positive, I want my spins to be positive. And then this term here is saying we want our spins to take the same sign. You know, we want to have consensus, let's say. And so by hand, you can compute the conditional distributions of updating xi will have this form. You know, because everything's symmetric, I can just do it for one coordinate. I get the whole story. And so we're going to want to compare what these conditional distributions look like as I modify the vector that I'm conditioning on. And now what's nice is that because our spins are binary, if I want to control the total variation distance between things, I can actually just look at the expectations, right? If I want to compare two Bernoulli random variables, I just need to know what probability they have of coming up heads. And so I can write down explicitly what the conditional expectation here is as a hyperbolic tangent of things. Okay, and so we'll move to the next slide to get our estimate on the influence coefficients. So, right, we bound by the difference in means, scaled by an appropriate constant because they're +1 and -1. So this mi of x is just this quantity here, the mean of the things that are not equal to xi, basically. And so, you know, we get this directly. Because tanh is 1 Lipschitz, we can do this. And then because mi of x and mi of y, actually we said x equals y except in one coordinate. So we know that the difference will be order 1 over n. And so we know then that we can sort of write down this influence matrix, and it's going to be 0 on the diagonal and c over n in every other element. Right? And so we can actually compute the spectrum of this directly. It's sort of rank 2 matrix, I want to say. But you can really do it very explicitly. And you get that if C is less than 1, so if the interaction strength is small enough, then the random scan Gibbs sample for a continuous time will have a spectral gap of at least 1 minus C. Okay, so as C gets closer to 0, you lose the interaction. Things go very well. As C tends towards 1, you're hitting a phase transition, basically. And a point that's worth emphasizing, because this is relevant for statistical mechanics and these sort of things, is that this estimate holds uniformly in n, right? So it's not just for small spin systems, it's for every spin system with sufficiently low interaction in this sense. Okay. It's worth mentioning that a priori applying the diversion criterion to the Curie-Weiss model doesn't necessarily make a huge amount of sense, because it's not local interaction, right? Everything is interacting with everything, and so we expect a bit of pushback somehow. But the model is sort of simple enough that it tends to work out here. Yeah, so you can apply it to other mean field spin systems where everything interacts with everything, but perhaps not symmetrically. So that's the Sherrington-Kirkpatrick model is one instance of this. In this instance, you actually see the technique is very poorly suited, and you get the wrong scaling with n, basically. Now, if you wanted to apply this to easing, so again, all of this is for Gibbs sampling. If you wanted to apply this to sampling easing models on sparse graphs, where sort of every vertex has at most d neighbors, say, this is very well suited, actually, particularly if d is small enough. So you get very good estimates in that case.
So for the easing model, how does it handle like phase transition?
So I think it depends. It gets it right sometimes and it gets it wrong sometimes. Essentially, the coarseness of the criterion means it can miss important information. So with this here, for example, if I say 3 regular graphs, you can have 3 regular graphs whose topology is dramatically different to one another, but you will get the same estimates here. So it could be the case that if you take the worst case over all 3 regular graphs, it's sharp, but in any specific instance, you could be quite a way off.
For or even just like a two-dimensional like easing model, like you know, like if I'd imagine like before the phase transition or after the phase transition, like it might be better adapted.
Yeah, so I think basically at higher temperatures, it works well. I don't think it gets all the way to the phase transition on the lattice, because I think basically the lattice has turned out to be harder than people expected. That's my intuition there. Yeah, that's good. Okay, so a slightly more continuous example would be if you have a Gaussian graphical model in which the precision matrix is what I would call diagonally dominant, in the sense that the entries on the diagonal of the matrix are bigger than the sum of the stuff that's off it, up to a certain constant, then the Debruchin criterion will hold, but then you're sort of really applying this sort of generalized result, right? That's okay. I mean, we know already the convergence of Gibbs sampling on Gaussian graphical models more generally than this, because of work of Gareth and co-authors in the 90s. But what's nice is actually that those results are not so robust to non-Gaussianity. It's like really in the Gaussian case, you can do explicit calculations and you know exactly what's going on. But once you add perturbations, it's not so robust. Whereas here, if I was changing the model to be a non-Gaussian graphical model where I still have some sort of strong log concavity and a bit of smoothness, this handles it quite gracefully. And so this is something I'm sort of gradually writing up. But the estimates are sort of fairly straightforward. Okay, that's some other spins. Okay, and so actually, we're right on time. Okay, so to give a recap on the basic examples, I guess some recurrent elements of the case in which things are very nice is either that your transition kernels have a large overlap in probability, right? The kernels are all going to land in the same set, and so things behave very well there. That's basically the minorization case. Or that you have large spatial overlap. And overlap's not really the right word here, but somehow everyone's sort of contracting into roughly the same direction, either with some deterministic function or some flow or something like that. And in those cases, if you can sort of perceive that in your problem, you're in good shape, I would say. Yeah, and it's worth mentioning, so with these examples we've talked about, there hasn't been too much resistance, really. Like in the convex potential monotone drift case, everything in the problem is helping you. And somehow everything is pushing you in the right direction. There's no bad regions. Everywhere is uniformly good. And the natural metric works just fine in these cases. We'll see in the subsequent examples that when you don't have this condition, you have to be a bit more flexible with the metric. I think that's me done for this section. Okay, so we can break till past. Cool. Thanks. I can take questions now or in the break as people.
Can you hear me?
Yep.
Okay, great. So I just have a question on the Poissonized Gibbs sample. So is there any reason why you have to use a Poissonized version, or is a normal Gibbs sampling enough?
No, normal sampling would be fine. I think it's which slide? It's basically it's easier for me to phrase things in this way with the continuous time process, but the analogous result definitely holds for the discrete time random scan.
Okay, great. Thanks.
Cool. Yep.
Is there a physical connection on the Curie-Spice model that you satisfy down the phase transitions as you mentioned?
Yeah, so I think in this case, the Debruchin condition gets the phase transition right. But I should probably check that, but I think it basically reproduces that behavior.
How does these contractive type methods like handle multimodal distributions?
So we'll see some examples of that. There are ways of doing it, but it kind of depends on what sort of multimodality you have. And I think, so one thing I have written down as an open problem is essentially to develop metrics which are well adapted to studying tempering and stuff like this. I think I've not really seen it done at all, let alone convincingly. I think, I had the thought that for things like parallel tempering, in some sense, if you reduce to the projected discrete problem or something like this, you're sort of sampling on a weird tree sort of thing. It's like at the highest temperature, you have this, and then you have little arms breaking down into each of the modes. And so I think that could be useful, but again, I've not really seen it done. Cool. I'll pause the recording for a bit then, and we can reconvene at past.